Let us look at proposition number 9 of book 10 of Euclid's Elements. The proposition says the squares on straight lines commensurable in length have to one another the ratio which a square number has to a square number, and squares which have to one another the ratio which a square number has to a square number also have their sides commensurable in length. But the squares on straight lines incommensurable in length do not have to one another the ratio which a square number has to a square number, and squares which do not have to one another the ratio which a square number has to a square number also do not have their sides commensurable in length either. Quite a big proposition. So let's break it down. So basically what the proposition is saying is that if A and B are commensurable in length, then the ratio between the square on A and square on B will be the same as the square of this number and square of this number, the ratio between them. So what it is saying is A square is to B square is equal to C square is to D square. Okay. And the next part it is saying that if A square is to B square is equal to C square is to D square, then A and B are commensurate. In the next case, it is saying if A and B are incommensurable in length, then A square is to B square. For that, there is no corresponding ratio of a number square to a number square. And the last case is the ratio of the square on A to the square on B. If there is no corresponding number square is to number square ratio, then the sides of the squares are incommensurable in length either. So let us take up these cases one by one. Let's take the first one. Let A and B be commensurable in length. Now, if they are commensurable, we know that the magnitude A will have a ratio with the magnitude B, which a number has to a number. So let those numbers be C and D. So we will have A is to B is equal to C is to D. Square on A is to square on B will be equal to A square is to B square. Why? Because similar figures are in the duplicate ratio of their corresponding sides. Similarly, square on C is to square on D is equal to C square is to D square. Remember, C and D are numbers and A and B are magnitudes. Now, in case of numbers, between two square numbers, there is one mean proportional number, and the square number has to the square number the ratio duplicate of that which the side has to the side. So that is the reason why we have square on C is to square on D is equal to C square is to D square. So therefore, A square is to B square is equal to C square is to D square. So if two magnitudes A and B are commensurable in length, then the squares on them have a ratio with one another, that the ratio which a square number has to a square number. Now the next case is the converse of this. So we start with the fact that A square is to B square is equal to C square is to D square. And we have to show that the sides of the squares commensurable in length. So now, if A square is to B square is equal to C square is to D square, remember A and D are magnitudes and C and D are numbers. If that is the case, then A is to B is equal to C is to. And if this is the case, that two magnitudes have a ratio which is the same as the ratio between two numbers, then they are commensurate. So here A is commensurable in length with B. Now let's look at the next case. Let A and B be incommensurable in length. If A square is to B square is equal to number square is to number square, A is commensurable in length with B. That's what this would mean, that the ratio of the square on A to the square on B would be equal to a square of a number to a square of a number, in which case A and B would be commensurate. But we are given that they are incommensurable. So which means A square is to B square does not have any corresponding number square is to number square ratio. And now the last case. If A square is to B square doesn't have a corresponding number square is to number square, then the numbers, then the magnitudes A and B are incommensurate. That is again pretty straightforward. If A and B are commensurable, then A square is to B square is equal to number square is to number square. But we are given that it doesn't have such a ratio of numbers. So therefore, A and B are incommensurable. We have taken care of all the 4 parts of the proposition. And that was proposition number 9 of book 10 of Euclid's Elements. Again, let me remind you, there is a link to a PDF book which describes all these propositions in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now.